Everybody.
Quiet,
please. Quiet, please. Mm-hmm. Okay, everybody. So today we're going to discuss a bit about utilities. We are recording for future viewers, and what I will do is summarize the work we have done and plans for the future regarding utilities. We've refined the utilities to a high extent, just like we have the modularity and the structures. We modularized all the utility systems so you can have a seamless build. So what have we done so far? Let me share my screen for everybody else watching it. Entire screen. Share. Okay, so you guys remotely can you guys all see this? Let's assume we are. So we are recording this. Let's do a slideshow. Excellent. Let's see. Am I gonna quit out of that if I? Do I want to?
No, you can press the ad. Yeah.
Great. Okay. Utilities. All right. So in the CDK Home 4 build, we documented everything to perfection. You can say, so actually this is all in a CAD. Like for example, you see the whole PV and electrical system with all the components, even boxes and wires. You have a plumbing system, fully CAD'd up, water system, etc. So you can actually click on these. These are clickable. And we're applying the same techniques to the current build, which is CDK Home 7. So the first favorite, of course, for any utility system would be solar energy. We've done that since CDK Home 1. We've done a bunch of solar cells, including building solar panels from cells themselves. We soldered the connections and put glazing on top of that and a backing. So we actually got a bunch donated like in 2007, where we built our own. Those are the ones that have been decommissioned since. They lived for a few years and then they broke because it's not easy to seal them. But it's also a thing that you can definitely start getting into PV manufacture itself, because solar is actually quite an abundant thing. It's silicon. Silicon. Where does silicon come from? Sand. So sand is abundant, just like we got fiberglass insulation, which people think is evil. There's silicon that does semiconductor magic, such as photovoltaics. So that's a great thing. So we've gone from CDK Home 1. This is what we did in CDK Home 4. That's the model you actually visited the other day in the summer. This is actually CDK Home 6. That's actually the former. This is under construction still, but this is the system we're actually going to build. So we got 3 sections of 12 by 20 house. This is actually the same house model under construction. You've got 3 strings of 9 photovoltaic panels for a total of 6 kilowatts, which is kind of our standard for all construction. These are the panels on a roof in the CDK Home 4. Some details about how you put them together. You got to ground them. You got to interconnect them. This is the inverter system, which comes from the roof. And it powers the entire house on the sun, except for the on-demand water heater, which is high demand, like 14 kilowatts. We don't have 14 kilowatts, so that's connected just to the grid. What we'll be doing in the actual workshop, we're going to be, like, for example, this is actually the kitchen section of the house we're going to build. So here we line up, okay, where are all the boxes? There's a whole load of different things, from higher power things like running the induction cooktop or stove, to smaller wires, fridge, smoke alarm, etc. So we're going to get into this kind of stuff, laying out all the wiring into the walls, and some of it we actually going to lay into the walls at the structural stage. So we're actually going to install some panels that have some electrical in them. You'll see how that is done. As far as the photovoltaic system, here's a diagram. This is actually all the components that we're going to install in the current build. So you go from the photovoltaics to a photovoltaic combiner to a DC disconnect to the inverter. You have a transfer switch that fuels an interior breaker box. You have the large load of the on-demand water heater. You start if you're connected to the grid, you have a power meter and an exterior breaker box, etc. So this is kind of like all the system components, including DC breakers. There's AC breakers in the main panels, a PV combiner. So there's a few elements here which we work with. That's the actual picture in real life. Some of the details. We're going to be working with photovoltaic connectors. They're called MC4 connectors. They're watertight, rainproof, weathertight kind of connectors that you can put right out into the elements to connect the panels. We also will do things like this. Basically, this is an example of a utility wall. Our kitchen wall will look kind of like this, minus the vertical plumbing, because this was for the 2-story house, CDECO Home 4, where you see the plumbing going up. It's all in the walls. And in the last build, the CDECO Home 4, I pretty much installed this after the structure, but there's no reason why you cannot you've got all the water with sharp bite quick connect fittings. You've got the broken line there corresponds to all the circuits we put in, which are hardly visible because they're small wires. There's the structural stuff. So these things these walls have, and then you actually see the blower, not the blower, but the vent fan from the bathroom in there. So you've got mechanical, electrical, plumbing, and structure. We call those quad modules, where you can actually put all of that into the module itself. But you have to be careful about, well, how do you interconnect it? And there's means to do that. With the water fittings, you can simply quick connect using shark bite fittings. With wires, the general strategy is you have to leave some kind of a pigtail from one module to the next, or put in some of the wires, like say wire up all the boxes in there, leave a pigtail out for main interconnection, or do the routing like all after the fact, where we leave a utility channel at the bottom. We do not puncture any studs. We use a utility channel where, instead of drilling through walls to save labor, to optimize the serviceability, put a channel at the bottom. The wires you can open that up. You can modify your wiring if you need to. So it's, for example, in the CDECO Home 1, we've opened up that we have a small utility channel, like a 4x4 cavity at the bottom of the walls, where, we've taken wires in and out of that and threaded new connections into that. So it's actually very convenient to do that. Modularizing that. For plumbing, these are actually all the main rough-in assemblies. These are visual bills of materials. You can click on all these parts to actually get this, like, what is that? That goes to Menards right there. So these are hyperlinked visual diagrams. Perfect stuff to include in our automation of the entire system. Like when we put this in CAD, potentially, Jackson, can you get add hyperlinkability to your software?
Yeah, try it.
Oh yeah, no, that I'm ever grateful. I think so. I think clap to Jackson, because I think what he's done already probably is going to save anywhere between 40 and 100 hours next time. Like, because we generate all that stuff by hand. So thanks, man. It's cool. This is mine. Yeah. But yeah, this is a very convenient way to transfer information. You've got these assemblies that are then built out, like here, right? But that's all there is. This is like all the main connections. And by the way, we simplify the heck out of this. That's all we have, like 14 PVC assemblies and some straight pipes between them. You can get the visual bill of materials right here, get all the parts, build it like that. For the water source, this is a diagram of the parts from the street service entrance, like when you get water from the water company. So you got a main valve, a check valve, a pressure reducer, and then you start your distribution, including an expansion tank, because there's hot water in the system, so you have to use an expansion tank. Otherwise, you'd start getting leaks. But it's a great example. This we did in the last workshop. We put it together in like an hour. A professional will take a day or two to do that and charge you a bunch of money for it. $2,000 right here, and you can do that for what's the bill of materials cost? I think it's. Do I say that here? No, it's like $250 or so here for the entire bill of materials that you do in an hour. Great, save yourself $2,000. So these are all the actual connections that we did. Like, for example, this is number 2 here is an old version of that water service entrance, and you see I've got all this threaded stuff. Like, look at that, there's threads there. And I'm like, okay, cool, I actually got a leak in that, so I had to repair it. But after that, I said, nah, let's just do this. These are all 100% shark bite fittings, including the pressure reducer, check valves, these all shark bites, which means you can connect them in a second. Push them in, done. No tools. You can
fix them in a second.
Yeah, and they're allowed. This is not funky. Like, codes allow this, and they allow it to be behind concealed walls, so it's not a problem at all. This is an example of all. Look at that, 11 PEX assemblies with 34 pipes in the entire system. So we're trying to absolutely strip down the complexity into the most common simple form. Plumbing, water distribution, shark bite fittings. This is all. You got a hose bib for the outside. You got tubs, toilets, showers, washer, dishwasher, etc. That's all. It's all in here. That's all it is. Okay, and this is a must know. Mark, did you experience this for the first time?
I've used them before.
Okay.
I'm the biggest fan ever of them.
This is it. Forget about anything else. So fast wiring. What's wiring about? Typically in standard outlets, you have to take your wire, strip it, and then like curl this thing and put it around a screw and then tighten down the screw. Well, here you stick in the wire, flip the lever down, and you're done. So this is so good. And then you can take it right out too. You can I think when you release that lever, you don't even have to use like a screwdriver. You release the lever and it comes right out. So it's actually not a stab, like a stab in push fitting. It's actually a lever fitting. Can we save the questions for the very end, or should we go? Can you write that down? Write it down, make a mental note, and then let's ask it at the end. But this is so cool. Just so much faster. I mean, Mark did the assemblies with quadruple boxes. You can just plug them. Tell us about it.
So rather than doing all that little work in the shop, we brought those assemblies up, all the outlets, and we had a few guys just assembly line, make all the wires for the 4 game boxes, and it took half hour. We did it up here in the warm, and then just takes minutes. Where it says the little stripping gauge, you just strip it to that length, and then there won't be any extra sticking out copper. It'll be just right.
And they have outlets on the back, so you connect one to the next one using the same method, and it's very neat and fast. So you can gang them multiply to any number you want. Yeah, this is great. So here's the standard route. I mean, that thing, you got to turn those curls and screw down that screw, all of that. Fast wiring is cool. So we do heat pumps. This is in this build, I would like to try this thing here. I'm implying this. There's one wall module that has the heat pump, but the trouble here was that heat pump actually went. There's the exterior unit on the outside wall, interior unit in the house. This time around, we're going to try to fit them one above the other, so we can literally do one modular panel that we build like in a controlled environment, just put it into the wall. How about that? We have the disconnect in there. We have an outlet for an exterior outlet as well. Might as well do that since we have power there. And both the interior exterior unit, there's complex in terms of mounting. The outside unit needs a solid mount. You need blocking within the wall. There's a lot of plumbing that comes from the interior and exterior unit. I mentioned it was wiring, it was water, it was refrigerant. So there's a bunch of wires there. So to do that in a controlled environment is a good idea. The scope of work is to one, you physically connect all the mount everything. 2, then you wire it up. Then 3, the major third part is you gotta vacuum pump the system to allow the refrigerant to escape into the indoor unit. Because typically these heat pumps, the way they come these days is the working fluid is under pressure inside the exterior unit. So you have to let it out. Just turn the valve and let it out. However, before you do that, you have to evacuate the interior unit because you have air in there out of the factory, air or nitrogen, but you need the refrigerant to displace all that volume. You have to be only refrigerant, so that you got to use a pump, a vacuum pump like here. Get yourself this for $129 on Amazon. And the secret weapon here is this. It's this tool which allows you to take out, there's actually like an air fitting, just like on a tire, which you connect to suck out the gas from the interior unit. This tool allows you to make and break that connection under vacuum. So it's I won't go into the details, but this is, once you learn this, you basically can open up a thing to be, and then evacuate the interior of the interior heat pump unit without ever like breaking the seal into the environment. It's all under pressure, like under vacuum actually. So there's a little skill involved in that. But yeah, that's the scope of work on a heat pump. We've done things like, this is a good idea you want to do for utilities. Like you can take any chest freezer. If you cycle it on and off, it's not a freezer, it's a refrigerator. Why does this work? It's actually not the fact that it's horizontal or it's got a top opening lid. The fact about chest freezers is they're extremely well insulated. So if you simply turn it on and off, here we have actually, like, this is actually what we did, like a little Arduino thing. It's a little Arduino in there that controls the timing on and off based on the temperature inside. But even a simple thing like an on-off timer where you just time it. Okay, maybe you give me like 3 hours every day that you refrigerate and the rest of it is off. So you end up using, the actual facts are 1/8 of the energy. So it's on for like a few hours, it's supposed to all day. And it's really good because a refrigerator that operates on 8 watts average power. Now you've reduced your power usage from, typical fridge takes about 100 watts. So 8 watts is much less, 12 times less. Why?
Why the difference between, like, why does a refrigerator use that much more power again?
Because chest freezers have really good insulation and refrigerators don't. That's the secret. It's not the fact that when you open a fridge, like heat comes out. It doesn't have to do with that. It has to do with the amount of insulation. Chest freezers are very well insulated, and this is just one of those hacks that you can do. It's down to the insulation value of the actual container. So the more insulated it is, the less energy you use. We've done a hot water heat exchanger from a hydronic stove. So this actually we have in CD Go Home 1. We've used it. Oh, this thing gets hot. It's so hot that we have to try to keep the flame really low because that's a very solid heat exchanger. So we ran hydronics off of that. We had a blower on that as well. This was a partial experiment into a dual pellet / firewood stove. How does that work? Well, you can put regular logs in there, or you can insert this blower assembly where you drip pellets into it so that front burner element is a pellet burner. We never got it to work. Well, we never tried. We never finished it. But that's a great idea, I think, to have we moved away from that because then we got into heat pumps, which are the reality of wood stoves is it's labor. You got to cut firewood and all that vast amounts of firewood. So it gets a little labor intensive, and just didn't have time for that. But we've done hydronics like this here. Now, good news. Yeah, you can do this with shark bites these days. So right now, if I were to do this hydronic system again, I would actually use shark bites as long as you keep the temperature below 200 Fahrenheit, which is standard. The quick connect fittings can be used for hydronics heating as well. So that's really cool. This is a system from CD Go Home. We call this the Micro House 3. This is what we actually had. The hydronic system panel with an expansion tank and pump. But let's talk about some more freaky things. So in the original house. Oh yeah, let's talk about some more things, utilities that we proposed initially in 2016 with the view of the Open Building Institute. But we proposed that a regular house would have photovoltaics. You have things like gray water gardens, maybe a pellet stove, hydronic heating, compressed earth blocks. But you can go actually much further to biodigester. We actually did in a CDGO Home 1 a separating toilet, which I'll tell you about that. But then you can let's talk about some of the things you can do with a Global Village construction set. What can you do with a 50 Global Village construction set tools and a CDGO Home? You can do this. So I talked about in another presentation about your house actually becoming a productive unit. So you produce your own energy, food, and goods and things. Yeah, why not? So the garage microfactory, if you have open source design for lifetime products, you got 3D printing and other cool tools that get you 10 times the value of Amazon. I think that the thing of open design applied to all those kinds of consumer goods that exist on Amazon is a real deal on a small scale. It's just a question of, do we have any decent design out there? We don't. So, like, for example, I mentioned the ozonator that breaks every 6 months. Well, you can do that yourself. Design a lifetime design one where you can very simply snap out the ozonator, the high voltage element if it breaks, because those things burn out. But open source toasters, dishwashing machines, and fridges, which people throw out very often. You can do this kind of stuff if at the limit of a garage microfactory. But with 3D printing, you can do that. So biodigesters are cool. So this is the front end of the biodigester. It is, because if you have a device like this, what is this thing? That's actually a macerator pump. This can send your waste uphill. So this is a pump like behind your toilet. You can do that, and then you can throw this stuff into a biodigester, regardless of where the toilet is, on the first floor, second floor, wherever. We did something like that actually ourselves. So we did a separating toilet in the CDGO Home 1. We have that. We use that. And then this pump here, the pump is a weak thing. After 2 years, it broke and we never fixed it. But this system here, the plumbing involved, allows us to take a regular flush toilet and convert it into a separating toilet. How do you do that? If you urinate, the liquids are actually sent into a separate line downstream, whereas if you do number 2, you activate the pump to send this into a biodigester. So if you just flush without activating the pump, you're going down the drain, and you can say collect urine as fertilizer or such. In the whole ecology, we're talking about no waste. You got ecological cities where circular material flows occur. But I think this is pretty interesting in the sense that the thing about toilets is that people want it to be normal. So we treat it as, what if you're even a normal person, normal consumer? Would you even consider something like this? Well, I think this would pass because it looks like a regular toilet, but you're actually turning that into a separating toilet. It's a regular flush toilet. It does not have like two exits like the standard separating toilets do. Is anyone familiar with separating toilets? Okay, well, you in a biodigester, you typically do want to separate, because urine is a ready fertilizer if you dilute it. But solid waste, you need to process to turn them back into fertilizer, if that's what you want to do with that. So fertilizer or biogas that you can generate with it. We did this biodigester. This is the actual build. You can see this on the wiki under biodigester. So this is, we designed, it's fully in CAD, so we can actually build this out. This is a working system, a 2-toed biodigester, and then we built it out. That's some of the plumbing. It's not that pictures here aren't showing the finished product, but you can download the full CAD and actually start playing with it. But the concept there is, concept, how do they work? It's a very, very simple concept. You've got effluent that goes into a container, and microbes generate biogas from it, and then you can collect the biogas, and then the effluent that comes out is actually real fertilizer. So you have both gas and fertilizer from the system. So it's not a big deal. It's not super high tech. It's not high tech at all. to actually run that as a fuel. You can compress it. You can run cars on it. So it is an interesting proposition, because if you don't have sun or wind, you always will have microbes doing their business. You will always have BS in the world that you can convert into high value gas and fertilizer. So I think I actually call the biodigester a missing link to solar photovoltaic feasibility, because the feasibility of photovoltaics is hampered greatly by the fact that the sun doesn't shine. It's an intermittent source of energy, and nobody has cracked that. This can crack it. No pun intended. Biodigester with automated operation. Now, to get these systems into palatable, commercializable form, I mean, you'd have to do some automation and things like that. So a ready design that's fully automated and robust doesn't really exist. I mean, we did not take our thing anywhere to a product release or anything like that, but we are interested in taking that to a standard feature in our homes. Okay, if you want, and we may not even ask, we just say, no, we put it in there because it's a good thing. But I mean, that would be an infrastructure change. Like, you'd have to either have community-based sewage treatment, or you do a small scale on your own, where you're collecting the gas and say you got propane bottles or actual connection to your car. Oh, it's not conceptually difficult to execute technically. Yeah, I mean, you got to get everything right. And the lifetime design issue must absolutely be addressed, because all these things are, fragile, and all of that technology is fragile. So you got to design it properly to be lifetime design. Not going to go too much into it, but that's the other side of it. That's, you can grow food on the other side with the effluent. Here we have tilapia fertilizing the plants with fish waste in a recirculating system, but there's no reason why your effluent from the biodigester couldn't be a part of the system to water the plants, and to fertilize everything in a greenhouse, to recycle waste into food. Solar hydrogen appliance, I mentioned that before, and I think it's inevitable, but in the Global Village construction set, we have universal power supplies, which can create your electrolyzer to split water. Electricity plus water equals hydrogen plus oxygen. I put the symbol for the well drilling rig, but think of a device the size of your fridge that's making fuel for your car, including high pressure compression to fight like 5,000, really high pressure, 5,000 psi. But it's a realistic option for fuel that it will be there in the future. I don't believe batteries can compete, because any kind of a chemical fuel is about 10 times the energy density of electrochemical batteries. So, I mean, batteries do not compete with chemicals, including hydrogen. Oh yeah, so under the sink, throw in your plastic pyrolysis machine. So we're talking about waste issues in this house, right? Like taking the plastic and perhaps shredding it, throwing that through a gasifier to convert the actual plastic into hydrocarbon fuels. Plastic is hydrocarbon fuels like gasoline and diesel in disguise. It's actually not a super complicated process. There are no commercial readily available machines that do that. That would break the system. Wire appliance, I get crazy and thinking about all these other things, like say you want to recycle using a small induction furnace. So the induction furnace is a part of the Global Village construction set, so is a shredder. Hey, how about like just spit out fresh metal from the waste metal that you have in your house? Why not? Okay, we asked about our wind turbines. Cool. Yeah, you can put a big one on your house. We have a 50 kilowatt wind turbine in the Global Village construction set. Hey, supersize that. Build one of those 1 megawatt wind turbines on top of your house. Well, that would require some structural changes, but then you'd be making $50 every hour, 24/7, 365. So you have a passive income stream. All right. Wind turbine. Oh yeah, then how do you build your wind turbine? Now I'm going back to the Global Village construction set. You shred waste metal to generate virgin steel by an induction furnace and metal rolling. Then how do you make this turbine? I'm saying at zero marginal cost. Well, from the scrap stream, you can then do what's known as wire arc additive manufacturing. It's a form of 3D printing where the filament is actually a welder wire, so you're making big, solid metal forms. I mean, you can. I was thinking for the tower of a wind turbine, you can just do like a big 3D printer that climbs up on itself to create that. That's that. Yeah, and then thermal batteries, I think, is a real big, hairy, audacious goal. I mentioned that 70% of all electricity used worldwide is water heating, cooling, and space heating and cooling. Water heating. So it's like worth $5 trillion. That's how much power goes, energy use goes into that worldwide. That's a big deal. So if we can replace that, but I mean, the thermal storage is huge. If you do some calculations, actually, I put a little calculation to note there. 31 biodigester totes, which give you, so just look at biodigester totes as a accessible medium to store heat in with hot water up to 120 Fahrenheit. But 25 Tesla Powerwalls are the equivalent of one tote, like of the 31 totes, or 12 days of storage if the sun is not shining. So like about 1-to-1 Tesla Powerwall equivalent of biodigester tote. Water has huge thermal mass. Wait, that sounds unreal. I mean, one Tesla Powerwall for a hot tote of water, the amount of thermal energy that you can store by going from, like, say, 60 degrees Fahrenheit to 120 Fahrenheit. Those numbers are actually pretty crazy. But if you think about it this way, this is like for just first principle, how much energy can you store in water? It's real. I mean, that's why thermal batteries can work. We've done a lot of stuff such as water catchment. That's CDCA Home 1. Had this diagram of what that system would look like. So we had a pond where the water goes. Now we can also pump the water from the pond. We had more totes. So this is the water system, the big pond we dug there. This is that's fresh after digging, so it's muddy. But then you can pump that water. You have a hydrant. We collect rainwater using a first flush diverter, which is when it first rains, there's a lot of junk and dirt in that. So you flush it. That's how it works. It basically fills up and the bowl closes it up like that. So we had that, and then we were collecting that in biodigester totes for water storage. So see that water going in, it lifts the bowl up, closes up the hole to divert the water into your actual storage. And then the water on the bottom part just weeps out through a small weep hole. So it's self-maintaining. So these are the cisterns. We still have the biodigester in there and the water cistern there too. We haven't installed the purification system fully, but we also did this. I mean, we were actually doing the separating toilet. We were collecting urine for fertilizer that you can then pump. There's companies that do that. Companies like eco-freaky companies that actually use urine as fertilizer. That's a viable thing, because urine, if you dilute it 10 times, it's perfectly safe to water plants with. This is what we had there. You can filter that rainwater through a system of filtration to get to potable water. I think ozonators are a cool idea. It's just high voltage. So once again, going back to very common non-polluting things, electricity generating high voltage sparks that turn O2 oxygen molecules into O3, which is ozone, which is highly reactive. It's like chlorine. It's basically the natural form of chlorine that purifies anything it touches. It kills bacteria and stuff like that. So that's a way to do that. And then now we're talking about reverse osmosis, i.e. desalination, that you can design in open source. Once again, with the idea that the key elements, the filters, they're high tech, but you can build all that. That's like that vitamin, the secret sauce. But around that is all open source lifetime design. In other words, if you get the key component, the actual cost of that key component is actually very low. And when I was looking at the price, you can build a $1 million desalination facility for 10 times less cost, because the filter material is much less than the actual. If you get a desalination plant from a company, they'll charge you a lot. What else we got? So propane or poopane from a biodigester can go right into your stove. Hot water systems. So I'm repeating this here. I'm not sure if I have anything new here. We did hillbilly heaters. This is a working idea, like things that work. You can readily turn water hot by running it in hot pipes inside a greenhouse like this. We did that to heat the pond. We've done a thermoelectric generator. So this is hot water from the stove. So this is when we were all into stoves before we went more funky into heat pumps. But you have the hot water from a stove, part of your hydronic system. Thermoelectric generators generate electricity from a difference in temperature. So there's a cold side and a hot side. They're not highly efficient. They're up to like only 4%. But if you have a heat source, 4% of a very hot source is still considerable power. We did that. We never took that to completion or anything like that. So I think that's, I don't have too much more here. The thermal battery is, as I said, the concept is, this is one of the tools in the Global Village construction set, the heat exchanger. We have that as part of the Global Village construction set. We were talking about the basic elements of technology where heat exchangers, we were initially thinking about that for steam power and boundary layer turbines, which it turns out they're actually very inefficient. And it's actually not as easy to build a regular car engine. It sounds like a steam engine would be much less complicated because they've been around. Like the first thing that came out were steam engines, but when you actually get one that performs, it's actually pretty hard. So we're okay with like diesel and regular engines, especially if you're your own biofuel like or solar hydrogen to run it. Yeah, so I think, I don't know, let's get some questions here. That's some of the main things. We talk about some of the practical things we'll also get into. Okay, go ahead.
Geothermal?
Oh yeah, geothermal. I didn't really cover that, but there's the main points about that is there's geothermal heat pumps, which take that relatively stable temperature and extract the heat or cool from that. The other way to do geothermal is you're just, say, for example, in the summer, you've got cool water at 60 Fahrenheit underground. So if you can dig your pipes underground like that and have enough length of it, like 1,000 feet, you have considerable cooling power just to run that directly in a heat exchanger to cool your house in the summer. But that doesn't address the humidity issue. You still have to have some dehumidification. But geothermal is basically tapping into the stable temperature. Yeah, and the biggest thing about geothermal, there's some startups right now that are trying to go way deep into the core, because like a couple of miles down, which is actually like apparently very, very hard to do, but to get pretty much unlimited power, because anywhere in the world, it's not location dependent. If you go down deep enough anywhere in the ground, you get hot temperature to the point that you're getting steam. So some companies are now talking about, okay, do that kind of geothermal, i.e. like steam generation from very deep underground anywhere in the world. I like the idea in principle in a sense that it's ubiquitous, it's highly distributed, it's doable anywhere. Also, it's actually really hard to do that, so nobody's done that yet in practice. Mm-hmm.
Our oil wells, we routinely dig down 10, 12, 14,000 feet, and the water comes back at 190 degrees. So it's not boiling, but it's hot. We play with the ideas of reverse organic Rankine cycle generators. Economics never really worked out, but it was a hot enough. We have that 190 degree water coming out of the water, 190 degree liquid temperature, 97% water, 3% oil, and then our ocean water is like 40 degrees, and so you had a really good temperature differential for doing.
How much does it cost to go down a mile or 12,000 feet?
$2 to $6 million.
Prices maybe don't add up. But if you have an infinite lifetime well, that would work out. For the amount of energy it produces. Jeremy?
I had a question on the stove working off of biogas.
Yeah.
So my understanding was that biogas is very similar to natural gas.
Mm-hmm.
It's also my understanding that a gas stove has a different orifice setup with propane versus natural gas.
Yeah, exactly.
So have you successfully being able to swap a stove between the two?
We never got to the point of burning the gas. So we never followed up on that. But yes, you have to change the orifice sizes because of the way the flame burns differently.
I don't think you'd be able to just use a valve and switch back and forth.
You can't switch back and forth. You'd have to actually switch the nozzles. So maybe if you have 2 burners on natural gas and 2 burners on propane, then you got it going on.
I'd probably, in this instance, I'd probably swap 100-pound propane tank with some form of like natural gas.
Yeah, but if you're on propane already, you use the same jets. No, the other way around. Wait.
That's what I'm saying. If you have the stove set up for propane, you can't just switch a valve and switch back and forth.
Right. But if you're set up to natural gas from the grid, you can switch naturally to your natural product. Okay. Go ahead.
Yes. I can't grow a tomato, but I'm very curious about the pros and cons of hydroponic gardens.
I would say aquaponic instead of hydroponic.
Oh.
Hydroponic is where you're feeding it chemicals that are just extracted chemicals. Aquaponic is more natural products such as fish waste or whatever else you're feeding it. Man, the productivity of these things is, I mean, the thing you saw here is insane. That I mentioned the figure that it's the fish themselves grow at a rate of about a pound or 2 in the 2,000 gallons that we have in there per day. It's enough to feed yourself. It's like 1 or 2 pounds of protein. That's crazy. These towers, 1,000 plants. 50 towers times about 25 plants. So you get 1,000 lettuces every month. It's insane. So growth rates, like natural productivity, is insane. So once again, this is the case that there is no scarcity. It works. Our experience with this has been very positive. Now, the thing that killed this off is that you're gonna have to get very serious about integrated pest management. This is not like if you're in a closed environment, that will be the challenge. So you have to master that. We never got that far. This is a perfect case for collaborative open development, and name one project that shares that info, like that has a commercial viable model. I haven't seen one. We'd like to create one so we can put one of these in front of every house. You can create a business, just like a food as a service, whatever. You subscribe to this thing, whatever. The productivity is there. It's about developing innovative business models to tap that. Yeah. Okay. Go ahead.
Okay. So I made a little $5 cracky hydroponic system.
Yeah.
Which I was selling for a bit, and I want to make more before Christmas as presents and maybe to sell. In which is basically just a hydroponics thing where instead of having an air pump down at the bottom, it uses evaporation to give the roots air. So slowly over time it will evaporate, and pretty soon you'll have a good thing of lettuce like this, this big around. But the thing is, it's very easy to set up in like 2 minutes, and then you don't need to touch it afterwards as long as you have a light on a cycle, which you can get those for under $10. And then another thing is,
how much did you make?
It was time for a contest to see who. It was called Karen Kubicki Night, and under that, and because of that, me and my friend who I was working with split $850, so we made $425 each. But then also the ones I sold, I think I sold over 50 of them.
The systems or the plants?
The plants, but it wasn't
systems. No, it's in a mason jar.
Yeah,
that was really cute.
But the thing was, I made like 50 cents per thing because I was selling them for $5 each. So maybe $25 from selling them until I started going to a few. I went to I sold them at a different place where I sold probably 20 or something, and I sold those for $10 each. So that's $100. My largest selling day.
Is it open source?
No, but it would be.
It is. It's the cracky system that you can look it up online. All the information's online. So he was taking an open.
I did redesign my own. I redesigned my own for price and performance, and a local hydroponics or local growing store helped me design it somewhat, and then I bought stuff from them, and I did a lot of the design work myself and found a few different systems, combined and looked for cheapest, did some experiments, and found out that if you don't use rock wool, it really doesn't grow nearly as well. And you get a tiny little plant half the size before it dies from a bad stem. But yeah, so that was one thing I did. And then also, isn't pea completely sterile? I've heard that before.
I don't know.
I heard that.
Like, I feel like what you I feel like from what I've heard before, you could be straight unfruiting plants and it would be gross, but it wouldn't make anyone sick.
It doesn't have urine. Like it's not gonna really do this. It doesn't have to
Yeah.
It's just a very
So it's
concentrated.
technically sterile in that sense.
So you shouldn't need to dilute it to 1/10 is what I'm thinking, but I don't know that.
The urine is very high in urea, which at high concentration is not good.
Yeah.
You want to do that so that you're feeding it like that this the right way.
Yeah.
But one person being on one proven plant is not going to kill it. But if you're routinely feeding that mixture,
Yes. Same thing with chicken poop. We have chickens. And then the last thing is the aqua or the not aqua, the hydro tanks or whatever, the big tanks that you heat up. Those are a lot cheaper and more dense in energy than the Tesla walls. But how much % of the energy you put in can you easily take out?
Like 60%.
Okay.
So you've got photovoltaics. First of all, we're talking about abundant energy from the sun. They're like 20% efficient, but because you're using a heat pump, then you're tripling that because the performance is really, you get 3 times the energy that you put in. So it's equivalent to stating about 60%. As far as the thermal efficiencies, yeah, I mean, I don't know the exact details. I don't have data on that, but the main point to keep in mind about that is that you're running from solar energy, which now it's like yours because you own the solar panels. Ben.
So did you say that the main problem with the aquaponics system was pest management?
Yeah. So for example, let me give you an example. We did hydroponics as well. I took the lettuce, first cycle, rafts on water with all the chemicals in there. Went to farmer's market, sold out made $100 in an hour, and I left home. But then the second cycle, wow, like thrips and aphids start getting you. So it's like if you have a concentration of monoculture like lettuce, you're gonna get killed. So here you got to be paying a lot of attention to high diversity, beneficial insects and plants, and all that. But yeah, that's gonna be an art. This is where, but once again, documenting all of that and making it accessible, I think can go a long way. Yep.
Collaborative ecosystems in the sense that I have heard of an aquaponics setup where you grow fish and plants and then also mushrooms. They have a light side for the plants and a dark side for the mushrooms, and a water wall they're heating. And that water wall can be a heat exchanger to generate electricity. But then also the collaborative ecosystem part is that you actually introduce natural predators for things like aphids. So if I have ladybugs that eat the aphids, and once they eat the ladybugs, and then you just keep on putting in until you have a whole terrarium.
Exactly. We put in praying mantises and ladybugs as some of the things we did. And we did the mushroom towers, the buckets with straw, stack them up high. Got a lot of mushrooms from that. Yeah, it's great. And I was thinking that if you have access to straw, that like your mushroom appliance, where for the mushrooms, you have to ferment. Like there's different ways to sterilize. You have to start with a sterile medium. One thing you do is you can nuke it with some whatever base or something. Another way is to ferment it, and then the mushrooms will grow after the fermentation has happened. You need to take out the water. So fermentation is a means to sterilize the whole thing. I was thinking of, and that's a lot of labor. Like, so imagine like a mixer that does the sterile mix for you, deposits it into buckets, and you don't have to worry about it And so you have your mushroom growing appliance that seeds your buckets for you and then recycles it. I think there's a lot that can be done. I mean, all this stuff is, you got to have some labor in there. Could be labor intensive. So designing highly efficient, optimized, or automated systems, there's a lot to be done there, I think. I mean, think about even things like there's FarmBot, for example. FarmBot, the open source planting robot thing. Anyone hear of FarmBot? Take that. So you can, in this system, labor is you got to seed it, you got to harvest it, you got to pest control it. The seeding part, easily automatable. Existing technology is the FarmBot. It takes seeds and plants them one by one in a tray, but then imagine more things like, okay, drones. So now the drone takes one seedling and puts it into one of those towers. That's a much more advanced, like computer vision, perhaps, kind of a thing. But I mean, a drone, you got one solar panel on the roof. The drone every day it like picks up one seed and plants one plant. Whatever. Like think of systems which can make it feasible, because this is labor of love. Traditionally, you have to be into this and get to understand it quite a bit to make it work effectively. I think that open information and automation can change the game on that. It's such that every single person can have something like this, where you get your cherry tomatoes and fish or whatever, vegetables, all of that, your salad, you should have all of that year round stuff. Yeah. Go ahead.
So you said that the other thing was a lot better because it's insulated a lot more.
What I was thinking.
So you can freeze it.
But why don't we just insulate the freezers so that the refrigerator? Why don't we just insulate the refrigerator so that's also more efficient?
How?
I don't know.
I don't know either.
Or then probably the refrigerator, they're expecting me to be opening it all day, and they don't really think they need to. But the chest freezer, people probably only
Good
open
point.
those once every week or month or whatever. Like we have one that we open once a
Exactly.
month because it holds over salmon and stuff.
Okay.
Good explanation.
And leave a bunch of stuff on top of that.
Andrew?
A question about the utility system. There are three questions. Is there anything that's non-standard in electric, plumbing, or sewage systems? Or is the whole system going to easily pass?
This whole thing easily passes. I mean, we're just using sewage into a sewer system. We're using photovoltaics. That's common, though you will get asked for engineering if you do a hybrid inverter or any kind of solar system.
At the Maysville house?
No, in Maysville, we have no building department.
Oh,
So,
right.
but we built it to code, to
Maybe a
IBC.
hybrid inverter.
We have a hybrid inverter there. None of this is like the water heaters. They're on demand. That's common. Electrical, everything out. Like the utility channel is not a big deal. What the inspector will look for is that you don't have any wires less than 1.5 inches from the surface, which this does, because you're just running the wires under a panel. But if you get a good inspector, they won't say anything. If you get a really picky one, they will, because they say, oh, well, what if somebody nails into it? Well, there's no nails in that area. So, but they might not go for that. So it's kind of one of those little gray areas. But utility channels are, common concept.
Are those behind the wall or on the wall?
They're at the bottom of the wall. We basically have drywall, have a little bump in there, second layer of drywall. I'll talk about that when we talk about the electrical. So you got a wall, you stop at the 1 foot level where the utility channel is. You put your wires running down there on the surface, no drilling. And that's the whole point, like no drilling, just lay your wires out, just staple them. You can modify that. So that's what we do.
They're not encapsulated in like a metal or plastic case. It's
Nope.
just drywall and the stuff.
Right behind drywall, but no nails there.
Is that picture that part of the module?
Yeah. Yeah, it is. So we build that out once. When we install the like when we put the walls up, we run the channel at that point. Do I have a picture? I mean, you saw it. Oh, I didn't even point it out at the house, but it's there. It's that house. If you remember, it had a sheet and then it had a little trim.
Oh yeah.
The trim.
There you go. Yes, that's exactly what it is. It's very elegant. I mean, modifiable. That's it. I love it. I wouldn't do anything other than that.
And what about the outlets?
Yeah, the only freaky thing is the
Because normal outlets also have you
Oops.
can hook the wire in, right?
Oops.
But isn't that often considered poor practice? Are these a different type of?
I'm sorry, I don't understand the question. Where did we do something freaky there? What do we do?
So the outlets you showed, they have there's holes in the back that you plug the wire in, right? Yeah.
What?
The Leviton outlets.
Oh, Leviton. Yeah,
Versus doing like a shepherd.
yeah. No, that's code approved.
Yeah, is that different from like most outlets you get at a hardware store also have holes in the back? Is that the same kind of mechanism, or is that a
Different mechanism. The standard one, which you poke it in, it's a stab kind of a fitting. It's not a lever like these Levitons. And the ones that you stab in the back, yeah, there's issues with them because sometimes you burn houses down with that. This is a different mechanism. It's actually a solid lever. It's different.
Interesting. Okay, so
It's like,
this type of house.
yeah. And what do we do? Let me show you this other detail, which is absolute necessity in electrical Wago connectors. These things. We use that. Does anyone know what that is? Oh yeah.
They use it in Europe. When my father-in-law comes over, he makes fun of people who put little hats on the wires. He always teases me for those.
These are much more like beginner proof because you can mess up by twisting the wires, and if you need to undo them, it's always a bitch when you've got like 4 wires, 5 wires twisted together.
Let's clarify why. Yeah.
Lego.
Let's clarify why these. So the industry standard is wire nuts. These hats that you spin. First, you cannot connect solid to stranded. It's very hard to do that. Second, it takes more time. Third, you damage the thing by screwing it on tightly. So this doesn't damage it. It passes all the codes for conductivity and all that and thermal performance. And it's fast. You snap it in, put the lever down. That's the same mechanism as in Leviton outlets. Love it. It's the equivalent of the shark bite for electrical.
That's what I was gonna say. All the
Yeah,
videos
exactly.
that dismiss shark bite, like there's a little bit of a learning curve there. Like some people forget to chamfer the top,
Okay.
put it in and do the depth gauge and things like that. But anytime you see somebody debunking shark bites, we were talking about this the other day. They'll put it under like 10,000 psi, and they're like, "Look, it busts at 10,000." Where the maximum you'll ever see in a house is,
Yeah. Yeah, exactly. Now
way far away from that.
So
One of those things where it's like the pride of soldering it versus.
yeah, it's inertia. There's industry inertia. It's new things coming up, and little innovations like this. They're all over the place, and housing can be more effective with innovation. Aiden? Okay, a couple more questions.
So just on your lifetime design,
Yeah.
so I just want to make sure I understand. So you try and design so that what you make can have an eternal life with proper maintenance. Is that right? Okay.
Eternal life, primarily by virtue of accessibility of replacement.
Does that include the whole machine at some point, or is the idea that the core should always be able to remain as long as you replace like accessory parts?
Yeah, I think modular, like cordless drill or power tool construction set. You have a thing that's got a handle and a battery and a motor. You can put all kinds of implements on the top of it, or you can even switch out. Obviously, you can switch out a battery, put a big battery on it, or a small one. You can have different handles for different purposes. So all the things being interchangeable. Now in design, you got frames, and you've got then other functionality upon which you mount on the frame. Yeah, the frame should be flexible too. That you can, like, for example, in the bolt together structures that we did, you can modify the frames by screwing more frame parts together. That's one way to do it. But frames typically maybe like, say for a tractor, like maybe design it so it doesn't change, so it's just one solid thing. But it would be a good idea to modify even at the frame level. Definitely like all the components, the things that you put onto a structure, you want to be able to, all the heads, the working tool heads, you want to have that be modifiable. But it's really that open blueprints and the fact that bolts and screws are accessible. Like if you try to work on an engine today, it's like there's going to be all these bolts that you can't access and stuff because engineers design them because they don't build them and stuff and don't maintain them. So they don't care about that. And that's for real. Like they don't care about that. So, but a good design would be, yeah, you can maintain it, readily just take out a part. And we actually call it 5-minute design in our work. I want to be able to change a wheel, change a motor out, change gears in like 5 minutes. So make a major revision on the design, the thing that I build in like 5 minutes. So turn like the wheel brakes or engine brakes. I can snap it out. So design it. Okay, so a few bolts, you take off a couple of bolts or something like that, snap in a new thing. So they have to be accessible and all that. But those very fundamental design points are just neglected. Mm-hmm.
So it would be like Harry Potter, like you get your wand and it's like with you for your whole life and you just kind of maintain it.
Yeah, I'm not familiar with how Harry Potter, I haven't watched it. But is that so? So Harry Potter's got
it's
that?
like you
what's
get
going
one
on there?
that you have for your whole life and it's like you becomes part of it.
Okay. Yeah, it's kind of like that. I like that. Like for example, I have these vice grips that are my favorite tool and they always work. Some other ones just like they break and stuff. Yeah, like that kind of stuff. Like make it good so it lasts and just much more resource efficiency.
Do you have the geothermal cooling? Did y'all actually install that?
We did not install the geothermal yet. So in this workshop, what we can do is, I mean, it's kind of nasty out there, but that means laying out a bunch of, in a simplest experiment, just simple 1-inch polyethylene pipe. 1,000 feet of that gets you about 10 to 20,000 BTU of thermal energy, like a heat pump.
Yeah.
About 1,000 feet of 1 inch can get so much cooling. Like say you want to run your cooling, whatever your air conditioner that gets you down to comfortable temperature. Well, you can get that out of the soil, like consistent, say 60 degrees. That's the goal. You bury it. You know, if you've got that temperature around, you can use that directly for the cooling part, for example. Yeah, that's an example of direct geothermal as opposed to geothermal heat pumps where they're just exchanging between the heat or cool underground and your home environment.
Would you put that pipe ever in the ceilings so the cool would come down?
Yeah, absolutely. I think you'd want to have heating in the ground because it rises and cooling in the ceiling. If you're doing like hydronic kind of a thing.
Have you ever tried solar heating with floor heating? Putting that in the
Haven't done that. That's a great thing to do. I mean, solar thermal is great. Mm-hmm.
A friend of mine did that, and it worked for about a year.
Yeah.
And it sprung a leak somewhere in the concrete. I mean, in the pipe, and she had to abandon it basically, which seemed like a major design flaw.
What would go into a hydronic system? So here we have a wood stove, there's pipes in the ground. Is it just some copper pipe wrapped around with glue and a pump? Or
Just take that module off the stove in our house, put it on top there, connect that to this, and that's it. Let's do it tomorrow. All right. No, we've got, so this thing, if you notice this, it's a module. That top heat exchanger comes off. The box is a separate thing. That's in our house right now.
Oh,
You like that?
yeah.
The drawer, it's modular design. So you can run,
really making it so more comfortable?
yeah, we should just take it out of there and put it in here and get the hydronics going. Yeah. You have to modify, you probably have to, that has the top closed. This one has the bottom box is an open top because you want to get the flames in there. Yeah.
Well, at least someone brought an angle grinder, right?
There you go.
There you go.
The hydronics in here, don't sweat it. Just I just use shark bites, no pun intended.
Your last question?
Okay, last question.
So, where this is a little bit off topic, but how do you power this building? Is it solar power or just like the grid? Or
It's the man.
The man.
exactly.
Grid electricity. Now we have 100 kilowatts of photovoltaics sitting in the piles. They're going on the hangar. We're gonna get automated transfer switches, so we have photovoltaic power in the daytime. We're running the whole campus here on that, and then we transfer switch back to the grid when there isn't any, until the point where we have other means to generate, whether it's solar, it's biogas, or hydrogen, or whatever that is, to wind or anything else. Yeah, I mean, an integrated system until we get an integrated system. But easy start is start with that photovoltaics and inverters. The weak part is the inverters, because they're going to break sometime and you have no control over that. It's like one little thing burns out, you throw it out. So open source inverter is part of the Global Village construction set.
Are you running shingles over there?
Like solar shingles?
No, for the hangar.
No, it's
a flat roof.
It's a flat roof with membrane material.
And gravel, right?
Membrane and then gravel covering that to protect it from
Is that what you
UV.
have on the Maysville home?
Exactly. And therefore you get no UV degradation, so the material underneath should last a very long time, like 100 years or whatever. Yeah. Okay, so I think we'll quit it here. So thank you, everybody.
Man.